proofs of equality, elements of identification types, and paths between points in spaces. And space can, let's for the moment just be naive and think that we're talking about topological spaces. So I've drawn a torus here, right, which here's a path from x to y, and here's another path from x to y, and we're going to think about this as somehow being a type, and the x and y as being elements of that type. And here we've got two different proofs that x and y are equal, if you accept that a path from one thing to another is going to witness the equality or identification of x and y. So what's useful about that is that when you start iterating, you're in familiar territory, right? So I mean, a path between two paths is a homotopy. So I've drawn a picture of, trying to indicate in my rather amateurish, non-animated pictures, transforming the path P into the path P prime through a homotopy. So we'll be living in this second order identification type. Whereas, I mean, in this particular case, you would not expect, right, and indeed there isn't, a path from P to Q, because somehow Q wraps around that way around the torus, and this wraps around the other way. And of course, I mean, that's the point of homotopy theory as a branch of mathematics, is partly to make mathematically precise things like that assertion that there is no homotopy between P and Q, and of course, a lot more besides. So if we draw up a kind of a chart, right, elements of identification types being like paths between points in a space. So then from that point of view, the proof of reflexivity is analogous to having the degenerate path, which just stays at x. That seems reasonable. Then Thierry was talking this morning about transport along proofs of equality. So from the homotopy point of view, then we're talking about transport functions in fibred spaces. So I mean, I've got my space A at the bottom, 2 points in it x and y, I've got a path from x to y, and I've got a fibred space over it. So this ellipse here is the part of the total space that's lying over x, and call it b of x, and this is lying over y, b of y. And on the logic side, we have a substitution function. If I have a proof that x equals y, and I have a property b of x, then I can use that data to get a proof of b of y by transporting from x to y along the proof p. Okay, and that's going to correspond in the sort of world of homotopy theory to having transport functions between fibres. So that's a familiar concept on the right-hand side, and corresponding to something in the type theory. And if you, because I'll need this later, if you transport along the degenerate path, which I've naughtily drawn as going from x to itself, it's pictures. You should never trust pictures, right? So this picture lies, right? Because x is supposed to be the same x. Anyway, it gets worse in a moment. What we'd either want to say that the substitution, the transport of b along that reflexivity is either definitionally the same as b. That would be a rather strong thing to do, and that's what you would sort of get if you were using original Martin-Löf identity types. We're going to sort of be a bit more propositional about it, and just ask eventually that for things where when you transport along the identity, you don't get exactly b, but you do have a proof of equality from b to the substituted version. So there'll be a homotopy in the fibre from b to the substituted version. So a sort of propositional version of the substitution property. Then there was more, right? Because Vygotsky, I guess noticed that the notion of path contractible space, so that's a space with a point, a centre, where every other point can be reached from the centre by some path. Okay, so if you think of the paths as the qualities analogy, that's saying that you have a type that has an element and every other element is equal to it. So it's saying there there exists a unique thing in your type. So places in type theory where you're trying to say there exists a unique X such that blah, 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 have something to do with path contractibility. And the point being that actually this notion of path contractibility from homotopy theory is terribly nice at organising exactly what is the right way of saying certain rather complicated things. So I mean, one instance of that, and it's the, I didn't know, by the way, where's he gone? Is he here? Yes, you are. So I didn't know that this axiom was discovered by Martin-Löf in 1973. I must read my papers more carefully. Okay. So what I've drawn a picture of is an example of one particular path contractible space. So it's the dependent product. So it consists of pairs, right? An element in A and a proof that that element equals this fixed X. Okay, so here's one element where the proof is reflexivity, so the Y is X and the REFL is, so I've properly drawn the degenerate path there. There it is, sitting at X, not going anywhere. And if you've got any other point in this sum, Y and P, so a Y and a path to Y from P, there's a path in this product space from the center to this thing. And you guys, you know, if I was a flash animator, I'd be able to now switch on my animation and this would grow, and you'd see this path growing up here, right, along itself, starting at the degenerate thing and ending up being the whole of P. So that's sort of why this sigma type is contractible. So you sort of follow along P, as it were, growing as it goes. So that's, I can't remember whether Terry mentioned this morning, but I mean, if we stop at that point, that's actually, in fact, characterizes identity types, these four things, this contractibility property and having a transport thing working nicely on degenerate paths and having degenerate paths and having identity types too. So it's an alternative way of getting at this kind of thing that you would perhaps more routinely see in terms of a computation rule, the J operator of the computation rule. And then there's univalence. So on the right-hand side, that has to do with the fact that I suppose if you're a homotopy theorist, then you only want to deal with properties which are invariant under homotopy equivalence. Okay, and so if you're going to take that seriously in the type theory, that means equals has got to always respect such properties, and that kind of ends up inevitably giving you this extensionality property that we were seeing this morning. So again, I've drawn a picture of it if you prefer pictures. A universe, here's my universe, right? It's a type whose elements are types. So here's a type X in my universe U, and I've drawn X there. So it's like a fibered space, but the fibers are, as it were, the types that are lying in the universe. So we know if X is equal to Y, if we have a path from X to Y, we've got this subst function that allows us to get a function from elements of X to elements of Y. We do the subst function to transport such things to such things. And of course, the properties of equality are such that that function from capital X to capital Y isn't an arbitrary function, it's a rather well-behaved thing. It's an equivalence, right? So there are different ways you can say this, but at least one way would be to say that for everything here in capital Y, there exists a unique thing in the pre-image that gets mapped onto it. And if we say exists unique using path contractibility, then we get the right notion of how to say equivalence in type theory. So every path between types gives an equivalence, and then univalence says that in fact every equivalence has to arise in that way. So that a univalent universe, it would be the case that if you had an equivalence between X and Y, it was because there already was a path between capital X and Y which induced it. So that's a very natural and interesting thing. So what I'm interested in is having some instances of this notion of univalence, okay, some models of it. So there are existing models, And I would say, and you can shoot me down in flames for saying this if you think I'm wrong-headed, but I really know only two different ones in the Feynman analysis of a univalent universe with, closed under all the constructs of Martin-Löf type theory, including equality and so on and so forth, and having universes in it and so on. One is in classical set theory with using complete simplicial sets, which Minkowski first pointed out. And now we have another one using cubical sets in constructive set theory that he and his collaborators have produced. Actually more than one, but one is slightly nicer behaved than the other. But I would say, right, from my point of view, I would like to see some more and possibly simpler ones, because with the best will in the world, these are not so easy to, if you took your 12-year-old and tried to explain in some detail why the universe was univalent in these settings, there's quite a lot to do, and it's not easy to do. And I can't really understand why not, because the concept is pretty straightforward once you grasp it. I mean, there are harder and simpler ways of saying what univalence means, but it's pretty clear, and it has this heritage of coming from extensionality that Kelly was explaining this morning. So I would really like to see more instances of this notion, and simpler ones. Right. So how are we going to find them? Well, I can't think of it. Yes, Steve.
You count the groupoid model as
no.
a submodel of that first one?
So I don't count the groupoid model as one, because it's not really a model in which you end up with a univalent universe that's closed and it doesn't have the full identity types and such like.
Then the universe of sets in the groupoid model is closed under all the type constructs of Martin-Löf and is univalent.
Yeah.
It just doesn't represent all types.
Yes, so I suppose that's what I mean. I want to have the full sort of high dimensionality in there. Right. Okay. See, I knew that somebody was going to say that. Didn't know it was going to come from the left wing over here. But, yeah. Okay. So the groupoid model is good. And I suppose actually what I would like for my more simpler one is that if you just sort of somehow could just do the infinity groupoid model, in a really simple way, which was evidentially a univalent universe, then that would satisfy me. But we don't frankly have that description at the moment. So what I was going to say is that I mean, how are we going to get any model? Well, you have to use category theory. Sorry, folks, but you do. Category theory is highly developed, both on the type theory side, in the sense that lots of people have worked on the kind of category theory you need in order to give a model of Martin-Löf type theory, and things that you might do within that in terms of categories, contextual categories, categories of attributes, categories of families, etc., etc., etc. And on the homotopy theory side, of course, there's all the stuff of categorical axiomatization of various homotopical things. So I'm thinking, in terms of factorization systems and equivalent model structures and so on. And those subjects, it seems to me, at the moment are kind of meeting and merging in interesting ways. So we have category theory to help us organise what is needed for a model. So you might hope naively, if I was explaining this to an undergraduate, that we could just take, they've just done a course on topological spaces and continuous functions and homotopy theory in that. Why isn't that a model of type theory, just as it stands, right? And unfortunately it isn't, because topological spaces are really bad from the point of view of the first two kind of higher ordernesses. So higher order functions and universes. Sure, with a bit of work you can kind of get some things working, but it's not very nice. And so we can't just sort of literally say that we'll get a model in which type is a topological space and a proof of equality literally is a continuous path, because the higher order things are not going to be so good. So that kind of was why, I suppose, partly Grothendieck, obviously generalised the notion of topological space, but for a variety of purposes in algebraic topology and algebraic geometry. But the fact is that his notion of space, so you take your topological space and you replace it by its category of step value sheaves, and then you note category has certain exactness properties, which that's all you need to know. You can forget that it came from a space and just remember that it's a category with certain nice exactness properties, and that's what a Grothendieck topos is, with generators and so on. The existing models, like the simplicial sets model or the cubical sets model, they are, living within particularly simple pre-sheaf Grothendieck toposes. So that's a good place in which to look at things. What we're doing is just slightly different, because the fact is that the constructions that you do in order to make a model using this kind of category theory, whether it's model categories or the semantics of Martin-Löf type theory, is pretty complicated at times, the constructs that one's making. And we have at hand a good tool for making some of that complication simpler to describe, namely logical languages, namely actually higher order logic and type theory in the first place, which is a convenient way of expressing certain things. So if you remember that you're in a topos, but you forget that it's a Grothendieck topos, and you just sort of, so Lorvier and Tim sort of formulated what aspects of Grothendieck topos is in terms of sort of finite tree axiomatization are needed to model, first of all, intuitionistic higher order logic, but then we know how to sort of interpret extensional type theory as well in there. You get to use the language of HOL and type theory in order to describe constructions that you can carry out within a particular topos. And that's can be much easier to understand, especially if you're not an arrowhead, a category theorist, in other words. If you don't live and breathe category theory, but you do live and breathe this kind of formal logic, then a lot of the constructs are perhaps easier to understand stated in those terms, and then interpreted in ways that we know back into the categories. So actually, we've been working with this internal language of a topos, so which is sort of higher order logic, intuitionistic higher order logic with meets extensional Martin-Löf type theory. So it is a dependently typed language, and trying to you might say somewhat naively, just pursue the idea of what is it that you need of the notion of path in order to get a model, a path-based model. So in other words, to actually turn the analogy that I've sketched into something which is just literally is the model of type theory. So we're supposing that you have an object in your topos, which is going to act like an interval. So it has two endpoints, I call them 0 and 1. So once we've got that, we can have path types, right? So which we'll hope will turn out to be identification types. So it's the same sort of formation rule, but the constructor, the introduction is that if you've got a function from the interval into some type A, then that's a path from what f is at one end to what f is at the other end. Okay. And we need to have some kind of transport or subs. So I'm going to, in this talk, take the simplest possible thing. So this is diverging now from what goes on in both the CAN simplicial sets and the cubical sets. I'm going to just take the absolute minimum, which is that and I'll call it a dulled vibration, which I think is probably a bit of an abuse of dulled, but it's not a bad name, I guess. So I'm thinking that we have for every path. So I'm going to look at families of types that come equipped with a substitution structure, meaning that if you've got a path downstairs, you're given a function between v of x and v of y, and when that path is constantly at x, then you have a path from b to where you're sent by REFL. Sorry, the data projectors in this place are not very good because they can't deal with modern resolution. So that looks really good on my laptop, but it looks bloody awful on the screen. Okay, so vibrations for us then will in this talk anyway, will be just simply that you have a transport function, and when you apply that transport function to REFL, you get something where there's a path from the original thing back to that. So the question then is what properties, if you go with me on that and say that I'm going to do, so this is a lot simpler than the kind of vibrations you see in the existing models where you have more complicated extension properties, right? This is a very simple kind of extension property. So correspondingly, it probably means that we're going to load more onto the properties of the interval in order for this to give us a model of Martin-Löf type theory in which identity types are given by this path construct. And we've been using Agda to explore, if you postulate some properties of the interval, can you do things like show that a vibration structure on this family and a family of such things, you can do a pi type or a sigma type or an identity type, can you construct a vibration structure on the resulting thing? Those kind of calculations we've been using Agda to do. So now I'm going to talk to you a little bit about what Agda looks like and how we've been using it. Okay, so Agda, right? So it's the Swedish chicken to the French hen. I mean, sorry, it's the it's the Swedish hen to the French cock. I mean, literally, right? So this is a product of the guys in Göteborg. And at its core, right, I mean, it's giving you the ability to do inductive definitions of index families of data types involving dependently typed functions, right? And the mode of operation is that how Agda assists you to construct elements of such data types is that you write down expressions with gaps, with meta-variables, holes, if you like. And then Agda will assist you to fill in those holes bit by bit, hopefully building up something which in the end is a term of the type that you are interested in. And it's from a theorem proving point of view, it's the usual story that we're regarding some types as propositions, and so proofs of those propositions tantamount to constructing elements of those types. Now, for me, it's these things in red which were the real clincher when I first started using this, because Agda provides these things in a really simple way. I mean, I did try and use some other systems like Coq, for example, and just found myself being able to more easily use Agda because somehow you're given direct and simple access to that. I mean, I was coming from the background of somebody interested in programming language semantics, and given the average age of the audience, I needn't say this, but if you've never tried playing with this combination of things, you really should be. It's like, sort of functional programmers' wet dream. I mean, there's so many things you can do. It's so expressive, it's so fun. All sorts of clever things that you can do with inductive definitions of index families of data types. And it's so much easier to do them if you've got a good ability to define the elements using pattern matching. Without pattern matching, I think it's hell, and with it, it's heaven. So, what do I like about Agda? It's just one language, right? It's very coherent. It's got a beautiful, flexible Haskell-like concrete syntax, which I happen to like very much. I mean, obviously that's a matter of very personal taste. So it is just one language. There is no separate tactic language, except actually the tactic language of Agda, as I would say, is eLisp, is Emacs Lisp. Actually, if you know what I mean, it's a joke. But unfortunately, it's not false either. But so that's all good. What's bad? Well, it doesn't have tactics. So that's bad, I suppose, if you like that. I mean, there are experimental uses of reflection to build tactics, but not as it were for the the standard released version of the thing. What else is good? Well, it's like Haskell. It rapidly evolves, and new ideas in proof theory and type theory get folded into it, perhaps more rapidly than some of the other systems. I mean, one should compare these, with Koch and with the new kid on the block, Lean. They're all, as it were, implementing Martin-Löf type theory in one way or another. So that's good. It's also bad, of course, because it means that the next version of Agda often breaks your code. But never mind. From the point of view of big proof, it's not entirely clear whether Agda can really cope with big proofs, right? So in my personal experience, and I'm not exactly the creator of very large proofs, but some of them are quite complicated, is that you can fall off the edge of a cliff in Agda without really knowing why. From a performance point of view, suddenly you go from doing something that takes microseconds to type check without using very much of your computer's RAM, and then suddenly everything blows up, and it can be very opaque as to what was going wrong. So it certainly does. There are performance issues which are a bit of a pain at times. What is nice, and it's nice for us for what we're doing, is that it's very easy to be unsafe with Agda. Right? It's probably true of Koch and Lean as well. I don't know, but what I mean is that we're very much not in the mode of Mike Gordon. So there's a sort of one view of theorem provers is that you should stick with a logical system that the theorem prover is providing you, which is everybody agrees is likely to be consistent, and that you shouldn't allow the user to get outside that system. So here we're very much doing things with Agda which probably allow us to prove true equals false, but that doesn't make it any less useful, actually. We're kind of experimenting to see what kind of results we can get. We're not doing, as it were, trusted verification of some important piece of mathematics or software or hardware. So it's a different mode of use. So what are the unsafe features that we use? You see, we have to make Agda act like it's the internal language of the topos. Don't need to do that in completely, but you do want to have, well, there are two kind of approaches. Agda itself doesn't have any impredicative universe of propositions. So you can fake one in various cunning ways. So Martin-Löf has one cunning way, which is where you basically allow a type of types encapsulated in one part of your code, and hope for the best that encapsulation really is encapsulating that use of a type of types and allow it to escape. And that allows you to do an important universe. We make postulates, in other words, we assert axioms, and we use something called trust me, which is a way of postulating inequality in a slightly computationally better way. And we use, Agda provides you with the ability to declare an equality, for example, to be a rewrite, so that some proofs become computations that would otherwise not be computations. And of course, arbitrary use of such things will very easily make the type checker not terminate. And that's probably the least of your problems. But it certainly is a problem. So you have to know what you're doing, I guess. I just sort of I thought I'd highlight the second approach here, rather than being impredicative, which is sort of what the language of a topos is giving you. You don't really need the impredicativity. As long as you've got quotient types, you can do most of what we need to do. So I thought I'd just show you, just so that I can show you some examples of Agda, how we're getting Martin-Hofmann's notion of a quotient type. So in Agda it looks like this. I mean, so we're postulating a type construct. It takes so set is like the first universe in Agda speak. The actual code is kind of polymorphic in universes, but on this slide I've suppressed that to make it more readable. So we take a type and we take a relation on that type, and we're asserting that we have a type which is the quotient of A by that relation. Don't need to assume that R is an equivalence relation. So if you like, it's the quotient of A by the equivalence relation generated by that binary relation. Okay. You probably want to use this postulated type construct together inside inductive definitions of other types. So Agda had better know that this construct is strictly positive in its first argument. It doesn't know anything about it because you postulated it, right? So here I'm telling it that it's strictly positive, and that would then allow the checks that Agda makes on data type declarations to do with strict positivity and hence termination to go through. So this is dangerous, right? Because it might not be strictly positive. I believe it is, but anyway, we're just going to say it is. And then we postulate, a constructor. So this is outside the sort of usual pattern of Martin-Löf type theory, because as well as having a constructor at the level of terms, we've also got a constructor of paths, as it were, or of equalities. So every instance of the relation gives you an equality between the equivalence class of X and the equivalence class of Y. And then elimination, how do I construct so I have a dependent family, predicate, as it were, on things of this quotient type. I want to construct a function out of that into this family, and the elimination rule says, well, you just say what to do on representatives, and as long as that function F respects the relation, so here's my subst, right? So I have to transport f of x, which lives in B of square brackets x, to B of square brackets y before I can say they're equal. So I'm transporting the usual. The usual identity type in Agda. So that's the elimination rule, and the computation rule follows from it like this. And then I'd like to sort of make that compute a bit more than it would otherwise, because it is just a postulate, just an axiom. So I make qcomp a rewrite, which just means every time Agda sees this left-hand side, it will rewrite it to that right-hand side. And that's, in this case, safe enough to do. And certainly make some of the proofs using this eliminator easier. So we're sort of in the logic of a topos, so it's like extensional Martin-Löf type theory. So I don't need to sort of do anything fancier here. If you're the sort of person who knows about higher inductive types, then we're not into that kind of thing. We're just assuming uniqueness of identity types, and so I don't need to say much more than this in order to get things working. But this one construct added is very nice, right? I mean, you get propositional truncation, if you know what that is, so you get existence and disjunction done in a way that if you go to Martin-Löf's talk in the workshop, you'll hear a lot about. You can prove function extensionality once you've got quotients. So that's all great. The downside, of course, is that you have to program with quotients using this eliminator, and that's a bit of a pain. And there surely has to be a better way of doing it, which I'll come out at the end of this talk, which is coming quite soon. Okay, so we add quotients, and then here's something that we can prove to answer this question. So I just want to give you an example theorem, okay, answering this line of inquiry about what sort of interval will give you a model of Martin-Löf type theory if you say that you're just going to use vibrations which are this very simple-minded notion of transport. Okay, so here's one example theorem. So let's look at so my notion of interval is the following. It's non-trivial, so 0 doesn't equal 1. It's connected in the logical sense. So if you have a decidable property of the interval, then it's if it's true at one point, it's true at any other point. And you have a total order on the interval. So the first three things, that's okay, right? I mean, there's nothing too bad about that. I mean, the delta 1 in simplicial sense would be an example, right? I mean, it's a non-trivial total order. It's actually the generic non-trivial total order, and it does happen to have this connectedness property. But we want a little bit more. It doesn't look like much. I want to have a binary operation of truncated subtraction, or modus, as some people call it. So that's minus with a dot over it. And modus, I don't need much about it. If j is less than or equal to I, I'd like I minus j to be less than or equal to I. Subtract I from itself, it should be 0. if you subtract j from I and then subtract that again from I, you should get j back again. So those are the only three things that we need. These are all kind of standard properties of a notion of truncated subtraction. So the theorem is that if you've got an interval with that structure in a topos, and you use this notion of double fibrations, a very simple-minded, just transport with REFL giving you a path rather than an equality, then you can show that that notion of fibration is closed under sigma types and pi types, that path types are identity types propositionally. You have disjoint union, 0 and 1, you have well-founded trees, and so on. So you get a very rich model of type theory. So all that has to, proving that theorem has to do with calculating that if you've got a fibration structure on this family, and it's indexed over another one, and you say form a pi type, how are you going to get the fibration structure on the pi type? Or similarly, how do you get the fibration structure for the path type itself? So we use Agda to help us with that, because some of the calculations get a bit complicated. I mean, neither Ian nor I are homotopy theorists, right? I mean, we're just humble, what would you say, computer scientists? Yeah. Okay, so it is very easy, if you're doing things with pencil and paper and you're working with paths, to get things wrong. I mean, this sounds a bit stupid, right? But it's very easy sometimes, if you're trying to construct a path between two paths, P and Q, to end up constructing something that looks more like that, where you've kind of forgotten that the bit at the beginning should be constantly x and the bit at the end should be constantly y. You say, oh, I've got this thing in two variables, I and j, that looks exactly like something that's taking me from P to Q, but then unfortunately it doesn't sort of. So Agda is very helpful there, because it becomes a matter of type checking, as it were, to make sure that you really are constructing paths between paths of the right sort. I'll just flash one example up, right? So you're not supposed to read this, but this is a proof, right? So I'm in the middle here of showing that the path types are fibrant, and what I like to do is, if I transport along REFL, so here's the REFL, and I'm transporting the path Q. Sorry, I'm transporting the path Q along the identity path. So that I'd like there to be a path from Q to that thing. So the conclusion here is I'd like to construct a path from Q. Twiddles is the path type. Okay. So I want to get a path from here to here under these hypotheses. And here I am constructing that path, and it's built up, you can see, as it's a composition of 1, 2, 3, 4, 5, 6, 7 subpaths composed together, and each subpath is built up. So it's a sort of chain reasoning kind of thing, and each subpath is actually constructed in a somewhat complicated fashion. And I don't think that there's any simpler way of doing it. The problem being that some of these things are paths which you might hope would just be definitional inequalities, but almost none of them are. So you really have to sort of do things in detail, and that Agda helps you a lot. I mean, obviously this is the result of filling some holes. You wouldn't want to read it, right? And if you wanted to reconstruct it, you'd probably rub it down and do it again. So that's where the tactic language is a little bit lacking, I guess. But nevertheless, it's you can smile and say, well, at least I have really constructed a path from Q to this thing that I'm interested in. Also, I would say, by the way, that this is a good example of falling off the edge of a cliff, because it's at this point, in fact, though this, it looks a bit complicated on this slide, it's not really very complicated, but Agda type checking that, unless you're careful, takes minutes and minutes and minutes for no real reason. Well, there is a reason. It's because there are hundreds of uses of composition of paths hidden in here, and each path composition is done in terms of this postulated quotient, and somewhere something is slow. So if you make the definition of path composition abstract, so it doesn't get recalculated, then suddenly it becomes a lot quicker. So there's a sort of a bit of nuisance with performance. So that's a kind of thing we'll be doing in Agda. What we're not doing in Agda is of course showing you that there are toposes that contain an interval with properties like this. But I mean, there are such things, but proofs of that at the moment are just things that we're doing in the paper. And what I'm, would like to have said is I have a model of with a univalent universe, but at the moment we don't. And it's because I don't know why we don't really. I mean, it's partly because the existing univalent universe constructions mostly are, well, they are to do with pre-sheaf toposes, whereas I don't think that you'll find a model of this theory in a pre-sheaf topos because of this stuff with numbness to work out so well. You need some kind of proper coverings in order to get the thing to work. So at the moment, we don't have, I can't show you as it were within this setting a model of univalence, but I don't also know any reason why we can't in the end, so it might be that we just have to try harder. I just want to end this talk by, I just want to touch on another aspect of this whole program, right, which is partly about kind of, this talk has been kind of in the foundations of theorem provers bit, rather than, because I'm a humble user of the theorem prover, I'm not an implementer of the theorem prover. But there's also the social exploration and curation of formalised mathematical and scientific knowledge aspect of this big proof program, right? And that does I'm interested in that because here I am as a category theorist, logician, computer scientist who used to know some homotopy theory but forgot it 20 years ago. I never knew very much anyway to begin with. How do I find out? Because there's a hell of a lot of interesting homotopy theory and algebraic topology there, some of it quite obscure. So one thing you can't do, I think, is just go to an expert and say, I have this problem, will you please tell me what I should do? Because that expert will know homotopy theory from his point of view, or her point of view, sorry, possibly, and may not know the obscure thing done 30 years ago that is just the thing that you need because you're doing something rather weird from the homotopy theory point of view. The type theory often makes kind of strange requirements that aren't, as it were, things that they would necessarily think of. So I don't know what the answer to that is. I mean, the answer I have so far is I search NLab. Right, so that's all I could think of doing. So this is the sort of the bastard child of Schreiber and lots of other people. And it is terribly useful. I mean, I guess you know. I mean, so NLab is this sort of collection of material about high-dimensional category theory and physics and philosophy and all sorts of stuff. And at the moment, the way I proceed is to search there and find some interesting pointers and then kind of follow them up. So the question is, right? I mean. You rely on the contributors to NLab telling you things which are true. Sometimes that's not the case. Of course, what they're not doing is giving you, in any sense, any kind of formalised thing. So you might see a reference to something, but you won't see a proof of it. You'll have to go off and kind of find that out yourself. So should we? I mean, is it even reasonable that we should try and have something like NLab which has a bit more formalised proof in it? I don't know really. It's probably not the most important aspect. What I think really
I proposed this as one of the topics for the workshop about the social structures.
Oh, good, excellent. I mean, the other point I was going to make, which from my immediate point of view, right, is the search aspect is pretty awful at the moment, quite random. And I'm sure that there are cleverer ways to trawl mathematical knowledge.
That's the other part.
You see, I mean, the thing is that NLab at the moment relies on humans to keep it going, and at some point they're either going to die or get bored. And it will stop, and it'll be frozen in time and won't be very useful. If we could create robots, as it were, that did it for us and kept on doing it, that would be really good. I have no idea whether that's possible.
There are things like that in other subjects like biology where you can actually populate databases from reading natural language.
Yeah.
So we've been working with Michael Kohlhaas to see whether their tools can be used on the NLab. It's currently stuck on a very silly issue, but we should try to get it done.
Yeah, but at least people are thinking about it. Yeah, and I mean there is some hope because I mean mathematical knowledge is it's not like natural language, right? And it's not even like biological science. I mean it's it should be a softer target in some senses. I don't know whether that's true though. But, you know, maybe it isn't actually, and especially not for things to do with geometry and yeah, maybe not. Yeah. So, but these are interesting, I think, things I would like to consume some of this. I don't think I want to actually create it myself. But, so that's pretty much the end of my talk. So, what I want, right? I want the world's simplest model of univalent type theory, and I haven't been given it yet, and I haven't managed to make it myself yet, but I still think it's out there. I would, on the theorem proving side, I really are quite taken and lean people. Is there a lean person here? So lean, I think, does provide quotients. Is that right? Yeah. So you need to tell me exactly in detail how it's doing that offline.
I think it's the ones you described.
All right. Okay. So the thing is that we have to do something with that, because you cannot continue to. I mean, quotients are everywhere, right? Obviously, it's kind of completely boring thing to say, right? In mathematics, you're always forming structures by doing quotients. But we're also then always defining functions out of their quotients by saying what to do on representatives and leaving the proof of respectability, or whatever you want to call it, to one side. And what I want, right, is something which looks like the truly wonderful dependently typed pattern matching that we have for ordinary non-quotiented inductive data types to work in some ways for quotients. Now, maybe the research on higher inductive types will help that towards that, but only if people bear this in mind. So one of the points of giving this talk is to say that it's no good telling me what the mathematics of hits are without also paying attention to allowing me to use them. Because frankly, inductive types in Martin-Löf type theory, nobody would be using them in a theorem prover if we didn't have Thierry's dependently typed pattern matching. I bow to him wherever he is. Yes, I bow at your feet. You may not like the fact that it gives you axiom K as well. No, I mean, no, it doesn't, right? But that one thing really allows you to use, you know, the richness of inductive types, and so it's terribly important. Yeah. And I don't know what I want, you know, on that last topic that I touched on, except I want to know exactly the things that I need to know, but I don't know what those things are or how to get them. So if you want to read some details, there are a couple of papers. There's some Agda code for in the kind of in predicative mode for stuff to do with the cubical model of Thierry and his collaborators. This paper is more like the kind of thing I was talking about today, but not exactly the same. And if you want to see the actual theorem I was talking about formalised in Agda, then I put it on my webpage here. Anyway, thank you very much for your attention.
So far, I would say also that if you use quotients, it would be nice to have a technique to the induction on, or I guess that this would be already helping to say, okay, I want to set up now a proof that I construct something out of the representatives.
Yes, that's really what I mean. It's easy enough to define a quotient, but it's not so easy to define when I say define a function out of it, I include in that a proof by induction, as it were, or, you know, because it's the same thing. Yeah, so it's giving the user, and it's not just that you define a particular equation and want to prove things out of it. What we really want to do is mix the definition of an inductive type with quotienting simultaneously. So you want what Torsten here would call quits, I think.
Yeah.
So, you know, mixing quotients and inductive data at the same time, and having a nice, so it's whatever the pattern matching is, it's got to be, you know, give you, if there were no quotients around in the ordinary pattern matching, if there are, gives you something that works. And maybe it's not possible to do, but I think there's probably something pragmatic that would be good enough, as it were, to get one a long way.
I mean, in Isabel, there is a package, for example, for non-free data types
Yeah.
But of course, it's in HOL, so it's a much simpler
Yeah.
environment.
Yeah.
Where you also have a way to define functions. So to define an inductive type with equalities on it.
Yeah.
And then you define a recursive function on it. You of course need then to provide proofs.
Yes. But Isabel sort of tells you what proofs you have to provide, presumably. So yeah.
Okay, help me out. I'm not trying to understand exactly what you want. I mean, so you need to define a function on the representatives.
Yeah.
And if the representatives are inductively defined, you're pattern matching on that. So that you already have. You can define a function on representatives.
Well, no, I mean, I mean, when you, the only thing you can do at the moment, I mean, if leave is the same, then that's all you can do as well, is that if I just put back the, I mean, to use QLim,
Yeah.
I have to supply a B, well that's easy, I have to supply an F, well that's easy, and I have to supply an E, okay? So I suppose I'm trying to define my functionality of the quotient, call it H, so H of Y will be QLim, B, F and E, where that's some god-awful stuff, whereas what I really wanted to write was H of square brackets Y is equal to blah blah blah, which is sort of like the body of F.
That is F. But then somehow you need to prove that it respects.
Yes.
I'm not trying to. Is it just that you want more automation for that?
No, I think there are ways of arranging the syntax so that it's what do I mean? So you'd make the quotient declaration look like a data type declaration, but where you say this. Well, you sort of you say these two things have to be
so
equal.
that's syntax. You do both steps at once.
Yeah,
You define,
yeah. I mean, I don't really know what I mean. Because if I knew what I mean, I'd tell somebody and they'd implement it for me. But there has to be, Actually, I mean, I think the problem is it's not. Probably it's. I think Ian, you thought about this a bit. I mean, it's probably not too much of a stretch to get something that works quite well just for a particular quotient. But if you're going to provide that wrapped into any inductive definition involving quotients, it gets more complicated. Different patterns. I'd like to have a product of two things, each of which is a quotient. So my pattern will be a pair consisting of two equivalence classes and blah blah blah, you know, and et cetera, et cetera. So it becomes quite complicated.
I really strongly agree with you that univalence is such a natural idea that there should be some simple models of it. The models we have are good for as far as they go, but
Yeah.
I feel like we haven't gotten to the bottom of it until
Yes.
we really understand why it's true.
Yeah.
Your approach of putting in an interval into a tuplos, for example,
Yeah.
and then trying to see, okay, what properties do I need on this interval
Yeah.
in order to make a model is something that I've thought about, as I told you before, with Michael Warren, and also it's the same or similar approach to the one that Richard Garner and Benno van den Berg
That's right. Yeah.
pursued with the path object categories. And in both of those cases, I think that what we learned was that it's hard to try to make a model in which everything is going to be a type, in which in which the interval has enough structure so that every object is a type. And so what we learned, or
which is what I'm getting, unfortunately, for free here, as it were, but it's probably too much.
maybe. But so the approach that I've been pursuing since then is put it in an interval and now try to balance two things. One is the interval should have enough structure so that some subclass of the objects behave well as types.
Yes.
And to look at what are the objects, what condition on the objects has to hold, so that those can give you a model of type theory when the interval has the structure. And one very beautiful fact that has come up is that if the interval actually just has 2 points which are distinct, then and you require the dependent types to be those families which have path lifting with respect to the interval, exactly in your sense, then you very quickly come up with the condition that you want to take those objects X for which the projection from the path space to X cross X is itself of vibration, that is, has path lifting.
Yeah, yeah.
And what that implies is the Kahn box filling operation. And that's I think.
Well, I would say that the
remarkable
Kahn
fact.
box filling operation implies that, but not the other way around, right?
It's equivalent.
I mean,
It's equivalent.
Um,
If you also close off under iteration, you want the path space of the path space of the path space.
oh, well, all right,
and so on.
maybe.
So that is, if you want to have sigma types and identity types, and these should be dependent types, and you require the dependent types to have path lifting, then that's equivalent to saying that the objects for which out of which you build the model are exactly the Kahn objects.
Yes, I don't know whether I fully agree though, because I mean, in our setting, we are getting that, and in fact, this code looks bloody awful, right? But actually, at the heart of it, all it's saying is that if I have a path here, P, and I have, the identity on X and the identity on Y, then there's a path there. It's the composite,
Sure.
It looks trivial, but I mean, but it's because you have to define composition of paths in a certain way and then prove certain properties of it. But that's not exactly, I would say, quite like box filling, because it is just that you have this path composition operation that you've been able to define. Been able to define it because of the
properties of the
integral,
integral.
yeah.
So you're getting it on all
Yeah,
that. Just an observation.
we should